is a slope field? That's what we're going to talk about right now. What is a slope field? Let's read what it says here. A slope field is a visual representation of the possible solutions to a differential equation. Remember that a solution to a differential equation is a set of functions or implicit functions, or if we have additional information such as an initial value, a specific function or implicit function. Instead of showing possible sketches of these functions, a slope field graphically illustrates the slope of the functions at specific points in the coordinate plane. Fascinating. Well, let's look at some examples. This kooky looking thing is a slope field that shows the solution to the differential equation dy dx equals 2x divided by y. In other words, each little segment, each little line segment tells us the slope of the function. For example, at the point 1, 1, that little line represents the slope, which looks like a slope of 2 maybe. At the point 1, 2, that slope looks a little less steep. Maybe that is a slope of 1. At the point 1, 3, that slope looks a little less steep. So if you kind of cross your eyes a little bit, you can use these slope fields to allow you to get a sense of what the solution to a differential equation might look like. Let's look at a couple examples. Here's a slope field, okay? And I gave you a point to go through. So what I'm going to do is I'm going to imagine sketching a function that I think would follow all these slopes and go through this point. So for example, I'm going to follow that slope, okay? I'm following that slope, I'm following that slope, and it looks like I'm getting less and less and less steep as I go. Whoops. Okay, just shifted that over, unfortunately. But you get the idea, okay? And maybe in this direction, my slopes are getting a little steeper, okay? So I just sketched a possible solution to the differential equation that is represented by this slope field. Now, if instead I'd gone through this point, well, maybe my sketch would look something like this. Right? You're kind of eyeballing the slopes. And those slopes give you an idea of what this function is going to look like. And again, this would be a function that would be the solution to a differential equation. This specific differential equation happens to be dy dx equals 2 times e raised to the negative x over 2. How kooky. Let's look at another slope field. Oh my goodness. This is a slope field that was generated from the differential equation dy dx equals the cosine of x. So take a look at that. I like to blur my eyes a little bit and to try to get a sense of what kind of function would fit in with these little slopes. I gave you an initial point there. So I don't know. This is a little kooky. Let me try. My slope looks good there. It looks like my slope, looks like my slope is 0. Now my slope is negative, 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 negative. Ooh, oh my gosh, it looks like goodness. If I'm following these little slopes, just kind of loosely following them, oh wow. What does that look like to you? Yeah, that looks like a sinusoidal curve. But if I had instead gone through an initial value of that point, I would have had a similar looking thing, but down here, right? Okay, so these are slope fields. And again, they allow us to get a sense of what a solution to a differential equation might look like graphically. How do you create a slope field? It's super easy, a bit tedious. Let's create a slope field. This is a classic differential equation dy dx equals negative x over 1. I just gave you an xy axis with a whole bunch of points, and I want you to create a slope field for these points. So stop the video and think about how you might do this. Well, when in doubt, pick some points. And in fact, that's how you make a slope field. That's how you make a slope field. I'm going to pick an x and a y. In other words, I'm going to pick a point, and then I'm going to find what the slope is. And I'm just going to make a little sketch of that slope. So for example, here's the point 1, 0. Here's the ordered pair 1, 0. Okay, I'm going to plug in my 1 for my x and my 0 for my y. Oh my gosh, danger! What does that mean at that point? That means the derivative does not exist there. That could mean one of two things. Either I have a vertical moment on my function or my implicit function, or it could mean the derivative just doesn't, the function doesn't exist. All right, so we're going to leave that blank. All right, let's try this point right here. That's the ordered pair 1, 1. So again, I'm putting a 1 for my x and a 1 for my y. That gives me a slope of negative 1. So right there, I'm going to eyeball and make a little line segment with a slope of negative 1. That's not that bad. Okay, let's pick this ordered pair right here. 1, 2. X is 1, y is 2. Okay, when I plug in a 1 for my x, negative 1, and a 2 for my y, I get a slope of negative 1/2. Okay, so again, you're kind of eyeballing it. There we go. Let's pick this point, ordered pair 1, 3. When x is 1 and y is 3, oh, okay, I'm getting less and less steep. You see how this is working? Okay, let's try some ordered pairs down here. 1, negative 1. Hope you're enjoying my little color coding here. 1, negative 1. So I'm plugging in a 1 for my x and a negative 1 for my y. Ooh, a double negative. Making me a positive 1. So my slope is a positive 1 there. And I'm thinking, let's see, 1, negative 2. You can kind of very quickly start to see some patterns and say, oh, okay, I think I'm seeing some symmetry. That's going to be positive 1/2. I'm thinking this point's going to be positive 1/3. So you're just going to be plugging in points here. And I think when you plug in enough points, you will start to see something interesting. So go ahead and pause the video and try to plug in some more points until you get a sense of what this is going to look like. Did you get something that looks like this? Now, I did this very quickly, but you should have gotten something like this, and that might give you a sense of, what do you think the solutions of this differential equation might look like? Yeah, if the solutions is an implicit function, it's going to be a circle with some radius, or a half circle if I'm just thinking about a function. So if I just quickly sketch, right, let's say I went this, my solution went through the point 0, 1, well then I'm thinking that my function, if it's a function, would look something like this. If it's an implicit function, okay, I'm doing a really bad job, but it might look like a circle with a radius of 1, okay? So this is a slope field, and this is how you create it. You literally just plug in ordered pairs, plug in the x, plug in the y, find the slopes, make a quick little sketch of the slope, and then if you're given an initial condition, you can eyeball it and make a nice little sketch for yourself. Again, tedious, but not that difficult. Here's a nice version of the slope field that we just did by hand, and you can see very clearly that this is suggesting what the solutions to this differential equation will look like. Either a semicircle or a half circle. Hey, let's just play with this. What do you think this differential equation would look like if it were just x divided by y? Let's try it. Drum roll, please. Ooh, interesting. What does this maybe look like to you? Yeah, a hyperbola. So perhaps a hyperbola would be a solution to this differential equation, or a part of a hyperbola if, again, we're talking about a function as a solution rather than an implicit function. You can actually go online and just put in slope field generator and play with these to get a sense of what these slope fields look like. And again, they are giving us a visual representation of what the solutions to these differential equations might look like. And that can be particularly handy because sometimes we might not be able to actually solve a differential equation. They can get pretty tricky, but we could at least get a sense of what the solutions would look like graphically.